Good day everyone. This presentation is for KIB2011 Biomaterials, Biomedical Engineering Semester 1 2025/2026. Our topic is the design of a hip implant. We are group 9 and our group members are I'm Kavitashri Anaparpan K. Tanabalan together with Yashwini Raghavendra Thayalan, Harini Vijayakumar, Nurul Shahana and Fatima Hussain.
Introduction. The hip joint is a ball and socket synovial joint that is formed between the head of the femur and acetabulum of the pelvis. This structure allows a wide range of movements, for instance, walking, running, sitting, etc. The joint is supported by ligaments, muscles, cartilage. This enables stability to be maintained by bearing the body's weight. Hip implants are needed when the natural hip joint is damaged or no longer able to function properly. Common conditions that require hip implants are osteoarthritis, rheumatoid arthritis, and avascular necrosis. The objectives of designing hip implants are: number one, biocompatibility. Materials should not be toxic and should be compatible with body tissues to prevent adverse reactions. Number two, wear resistance. Components should be wear resistant to avoid implant failure and reduce debris. Number three, mechanical strength. Implants should be able to withstand high stresses and loads during daily activities. Finally, longevity and safety. Implants should function reliably for a long time with minimal risk of loosening or complications.
Hi, this is Fatima, and I'm just going to go through the main components that make up a hip implant design. And over here, there are three photos, one of them being a diagram, the second one being a sketch that is labeled, and the third one being a realistic photo that is labeled as well. And let's go through each of these parts one by one. So first of all, we have the longest part over here, which is the femoral stem. It basically sits inside the femur, which is basically the thigh bone. And on top of that, we have the femoral head, which is the ball part of the joint. And then this part here is the acetabular cup, and it goes into the hip socket and replaces the original socket of the joints. And inside the cup, there's a liner which sits between the cup and the femoral head. So now I'll just go through what each part actually does. And starting with the femoral stem, this is basically the main support of the implant. It helps carry the body's weight and keeps the implant stable inside the thigh bone itself. And next we have the femoral head, which is the ball part. And it is what allows the movement and the hip joint, like let's say when you're walking or sitting. And then the acetabular cup replaces the original hip socket, and it holds the femoral head in place so that the joint can actually move properly. And then finally, the liner sits between the cup and the femoral head, and it mainly helps, let's say, reduce friction and wear when the joint is moving. So for hip implants, there are a few different design concepts, mainly cemented, cementless, and modular designs. So first off, we have the cemented fixation, and this uses bone cement to hold the implant in place, which gives immediate stability. And it's usually used in older patients or people with, let's say, weaker bone quality. And then there's cementless fixation, which doesn't really use cement, and instead it relies on bone growing into the surface of the implant over time. And because of that, it's more commonly used in younger patients and gives long-term stability. And lastly, there's modular design, where the implant is made of separate parts, let's say the stem, the head, the liner, and it allows surgeons to adjust size, material, and it also makes revision surgeries way easier if needed.
I'm Kavitashri Anaparpan K. Tanabalan. I would like to explain about material selection and fabrication. For our hip implant, we selected material for each component based on mechanical performance, biocompatibility, and long-term durability. The femoral stem uses titanium alloy for high strength and corrosion resistant. The femoral head is ceramic, which ensure low friction and wear resistant. The acetabular cup is made of titanium alloy as the outer shell for strength, while its inner liner is UHMWPE, which means ultra high molecular weight polyethylene, providing a smooth surface for the femoral head and minimizing wear. These materials together maximize implant lifespan and patient safety. Then I would like to continue on fabrication methods. The fabrication method is critical to ensure mechanical integrity and surface quality. The femoral stem is machined and forged for precise geometry and strength. The ceramic femoral head is sintered, producing a hard, smooth surface for articulation. The acetabular cup is compression, molded, and machined to achieve uniformity and low roughness. Implants also have hydroxyapatite coating to enhance bone integration. Now, let's look at degradation consideration. We also consider how these materials behave in the body over time. Titanium alloy resists corrosion in body fluid. Meanwhile, ceramics are chemically stable and wear minimally. Polymer like UHMWPE, which is ultra high molecular weight polyethylene, can generate wear debris which may cause inflammation, so we optimize their properties for low wear. Overall, the combination of these materials ensure long-term stability, biocompatibility, and patient safety.
So first, I'll be talking about the mechanical characterization of hip implants. This basically tells us whether the implant is strong enough to survive inside of the human body. For tensile testing, the implant material is pulled apart to see how much force it can handle before it stretches or breaks. This simulates the kind of stress the hip experiences during walking, standing, or sudden movement. It also helps us measure important properties like tensile strength, stiffness, and elasticity. Next, on to compression testing. Compression testing looks at how the implant behaves when it's pushed or compressed, which is what happens when the body weight is transferred through the hip during standing, walking, or sitting. This helps us check whether the implant can safely support the patient's body weight without deforming or collapsing. Lastly, fatigue testing is used to simulate long-term use. The hip implants experience millions of loading cycles over a person's lifetime, so this test repeatedly applies force to the implant to see whether small cracks or failures develop over time. This helps predict the long-term durability of the implant. Together, these three tests make sure that the implant won't suddenly fail under real movement. And next, we look at the surface characterization, which focuses on how the surface of the implant interacts with the body. Scanning electron microscopy, better known as SEM, is used to closely examine the surface of the implant at a micro and the nano scale. It also allows us to see surface roughness, porosity, wear debris, and structural features that cannot be seen with the naked eye. This is important because surface roughness affects how bone cells attach to the implant and how well it integrates with the surrounding bone. And the contact angle test is also really important because the test measures how liquid droplets spread onto the implant surface. This tells us about surface wettability. A lower contact angle means the surface is more hydrophilic, which is better for cell attachment, protein absorption, and osseointegration, which is the bonding between bone and implant. So SEM tells us what the surface looks like, while the contact angle test tells us how the surface behaves when it comes in contact with biological fluids. Now to compare SEM with optical microscopy. Why is SEM typically preferred? Optical microscopy is useful for general surface observation, but it has limited resource resolution. It cannot clearly detect very small cracks, pores, or wear particles on the implant surface. SEM, however, provides a much higher resolution, allowing us to see micro and nanoscale surface features. It can detect tiny defects, wear debris, and surface morphology, which are critical for evaluating implant quality. Why is SEM preferred? Because it gives us a more detailed and accurate surface information. It allows early detection of surface defects, which helps predict implant failure. Because of this, SEM is widely used in biomaterial research and implant quality control. In short, SEM basically gives us a much clearer and more reliable picture of how safe and effective a hip implant will be inside of the human body.
For this slide, we're going to focus on chemical and polymer characterization, which is crucial to ensure the materials used in hip implant are chemically stable, safe, and reliable over long-term use. Chemical characterization is mainly used to confirm material composition and purity, as well as to detect any chemical degradation that may occur once the implant is exposed to body fluids, oxygen, and repeated mechanical loading. One of the important techniques used is Fourier transform infrared spectroscopy, FTIR. It helps identify functional groups present in polymer materials such as ultra-high molecular weight polyethylene, which is commonly used as the acetabular liner. It is particularly useful in detecting oxidation products such as carbonyl groups, which indicate chemical aging. Oxidation can reduce wear resistance and increase the risk of implant failure. Another key technique is GPC, which is also known as gel permeation chromatography. GPC is used to measure the molecular weight and molecular weight distribution of ultra-high molecular weight polyethylene. A decrease in molecular weight suggests polymers chain scission, which weakens the material and increases wear debris formation. In addition, chemical analysis of polymer wear debris is important because these particles can trigger inflammatory responses, leading to bone resorption and implant loosening. Understanding the chemical nature of wear debris helps improve material design and longevity. Overall, chemical and polymer characterization plays a vital role in quality control, material validation, and regulatory compliance. When combined with other techniques such as scanning, electron microscopy for surface analysis, and instrument testing for mechanical properties, these methods ensure that hip implant materials remain biocompatible, durable, and safe throughout their service life.
In conclusion, the hip joint plays a vital role in supporting body weight and enabling smooth movement in daily lives, such as walking and sitting. When the joint is damaged by conditions like osteoarthritis, rheumatoid arthritis, or avascular necrosis, hip implants provide an effective solution to restore function and relieve pain. Modern hip implants are designed using strong, durable, and biocompatible materials to ensure long-term performance, safety, and improve stability and mobility. In the future, advancements such as smart coatings and bioactive layers may further enhance implants performance by improving bone integration, reducing wear, and lowering the risk of complications, leading to a better long-term outcomes for patients.